Hello everyone, welcome to the control systems. This is part 1 of lecture 9, root locus techniques. And this is the outline of today's lectures. We begin with the introductions and then we will define root locus and study its property. We also learn how to sketch the root locus by hand, which is the boring part. And then we'll learn to use MATLAB to plot the root locus, and this makes life a lot easier. Last but not least, we'll discuss the root locus for positive feedback systems. And if you want to have the slides, you can get from this link. And for further reading, please refer to these two textbooks. Okay? Control System Engineering on Chapter 8 and Modern Control Engineering Chapter 6. Okay, so let's begin with the introductions. And this is a definition of root locus. Root locus is a graphical representation of the closed loop poles as the system parameters vary. Okay. For example, if we consider this closed loop system defined by these transfer functions, and then if you recall, the stability of the system depend on the location of the pole. This polynomial function in the denominators. Okay, and in this case, the poles are not immediately known without factorizing these denominators, which is a function of this parameter k. So we do not have any knowledge of the system performance unless we factor the denominator for specific value of k. Okay. And the question can also be asked, for example, what value of k should we choose to achieve the requirements? And what is the effect of varying k for on the system? Okay? And root locus will be used to give us a plot of the location of the pole of as a function of k. We change the parameter value k. Okay? And by the end of this class, you will be able to state the property of root locus. You will be able to sketch a root locus by hand and use the computer program to plot the root locus. And you can also sketch the root locus for positive feedback system. Okay, so let's state the control system problem. For example, if we consider a typical closed loop feedback control system below, have a input OS, the output CS, and this is the forward transfer function KGS. This is the feedback transfer functions, and you can use the block diagram technique to combine this together. Okay, then you will end up having this transfer functions, the closed loop transfer functions, which is the function of k. Okay, so the poles change with k. So now let's define something. So if we define gs equal ngs over dgs, n stand for numerators and d stand for denominators of this gs, and also hs is defined like this. And then you can find the closed loop transfer function ts by substitute this two into these equations. Okay, you will end up having these transfer functions. So as you can see from this function, the system transient response and stability will depend on this k. Okay, because the system transient response and stability depend on the pole, and the poles has the functions of k. And again, we do not have any knowledge of the system performance unless we know the value of k. And we will get back to this later. So let's review a little bit about mathematics that we'll often see in these lectures. Okay. First, it is a vector representation of a complex numbers. Let's say we have a complex number s equal sigma plus j omega. This function described in a Cartesian coordinate can be graphically represented by a vectors shown in this figure with the angle beta and the magnitude m's. Okay, and if we consider these complex functions, this is a complex function, and if we substitute this s into this function, and graphically it is shown right here. So if you substitute this s into s, you will end up having a new complex numbers shown again in these figures. Okay, with the real part sigma plus a, and the imaginary part is j omega. And then as fs has a 0 at minus a, okay, from these functions. So if we translate the vector a unit to the left, we have an alternative representation of a complex numbers originated at 0 of fs and terminates on the point s, okay, as shown in these figures. Begin with minus a and then terminate at this point. Okay, now we can conclude that s plus a is a complex number and can be represented by a vector drawn from the 0 of the function to the point s. For example, we have the complex functions s plus 7, and if s equal 5 plus 2j is a complex, this is a complex number drawn from the 0, I mean minus 7 to this s, which is depicted in these figures. So you can apply the concept to a complicated function. So assume the function, a complex function fs defined like this. Okay, and then the function define the arithmetic, the complex arithmetic to be performed in order to evaluate fs at any point s, with the magnitude given by these equations and the angle given by these equations. For example, we have this function fs given like this. So find fs at the point at this point. Okay, so you can draw it in a complex planes. This have the 0 at minus 1, this one, and the poles at s equals 0 and at s equal minus 2, shown in these figures. If you do the math, s at 0 minus 1, this is the magnitude and this is the angle. You can use the previous this definitions. Okay, and at 0, at the pole 0, this is the magnitude and this is the angle. At the pole minus 2, you can compute and we'll end up having this magnitude and this is the angle. Okay, using the previous formulas, this formula, so you can compute the new complex number which have the magnitude of 0.217 and the angle minus 114.3 degree. Thanks for watching this video.